Sagorika, as you may have noticed that in the context of a general block design, the concept of orthogonality is a bit tricky. Orthogonality presupposes that every Nij has got to be strictly positive, and therefore every block has to have a minimum size equal to V. And if the block size is V for all the blocks, then it reduces to an RBD. Therefore, in order that we go beyond RBD, the blocks have to have minimum size more than V, and as a result there is a resource constraint. Therefore, this thing is hard to achieve in practice. So, on the other hand, the connectedness is a very important concept. Without the condition of connectedness, we fail to estimate the individual treatment differences, and therefore we cannot go for any testing problem involving the treatment differences. So, what is more desired is connectedness rather than orthogonality. Therefore, it makes sense studying non-orthogonal connected block designs. It's a huge area, there are a lot of results are there, but we will take up a very special kind of non-orthogonal connected block designs. This family of designs is called balanced incomplete block designs, abbreviated as BIBD, and that is going to be the topic for this module and for the next module as well. So, we will take up a study of BIBD with all seriousness. As I said, now we are going to take up a very special subclass of block designs. To start with, these are non-orthogonal but necessarily connected. As I told you, the importance of connectedness of a block design cannot be ruled out, because it is only then that we can estimate all the treatment contrasts differences or all the block contrast differences. So, that is a must. On the other hand, if we have resource crunch, scarcity of material, we can forego orthogonality and be satisfied with a non-orthogonal but yet connected block design. That is why that is our starting point. More than that, these are binary designs, because if there is really resource crunch, we do not mind taking Nij equal to 0 or 1, so long as the connectedness is retained, and hence the incidence matrix admits of 0 values as well. We are in the framework of a binary non-orthogonal connected block design, thereby ruling out an RBD straight away. Such designs form a special subclass of binary proper equireplicate connected block designs. Let us try to understand binary because it is 0 or 1, proper because we take all the block sizes to be equal, equireplicate we even take the treatment replications to be equal, and we want to make it a connected design. So, we now study a subclass of binary proper equireplicate connected block designs. Recall that we are in the framework of a constant block size, say k. So, there are B blocks, each with k, block size k, and then B into k is equal to total number of experimental observations, and if there are V treatments, assume B into k to be divisible by V, you write Bk equal to V into R, and that is the constant replication of every treatment. And these design parameters are such that there is a connected non-orthogonal block design. As usual, therefore, we start with V treatments in a block design involving B blocks, each of size k. As I said, the total number of observations small n is equal to Bk, and we assume it to be divisible by V, as I said. Therefore, we write R for the constant replication number. Note that a binary block design with k equal to V is identified as an RBD. Therefore, to exclude the RBD case, we assume henceforth that the block is incomplete in the sense that k is strictly less than V.
Sir, in that case, we necessarily have R less than B, since we have the identity n is equal to Bk is equal to V into R. This is also clear from the fact that we are dealing with incomplete block design. I am curious to know about the special subclass you are referring to. Does it have anything to do with the incidences of treatment pairs across the blocks?
Yes, right you are. Note that so far we did not mention about the joint occurrences of pairs of treatments. Is it the same for all pairs? That is a natural question that comes up.
So this may not necessarily happen. It must call for extra conditions on the design parameters. I believe.
Let's investigate. If all treatment pairs occur equally often across the blocks, we will really have a special structure of the incidence matrix capital N.
Okay.
The matrix capital N must be such that it entails us to view all treatment pairs coming equally often across all the blocks.
Okay.
Let us call this extra parameter the number of times a treatment pair comes across the blocks, constant number. Let's call this parameter lambda.
Okay.
Can you visualize this?
So let me try to say something, since I can see something. Within each block there are k treatments, all different. So that we have k into k minus 1 by 2 pairs of treatments formed. All the B blocks taken together, this leads to bk into k minus 1 divided by 2, total number of formations of treatment pairs. Again, since we are talking about V treatments and each pair occurring lambda times, we have a total of lambda into V minus 1 whole thing divided by 2 pairs to be formed. So therefore, we must have B into k minus 1 is equal to lambda into V minus 1. However, we already know that Bk is equal to V into R, and so it amounts to R into k minus 1 is equal to lambda into V minus 1. Sir, what if the design parameters that are B, V, R, K do not ensure that lambda is equal to R into k minus 1 divided by V minus 1 is an integer? Take for example B is equal to 12, V is equal to 10, K is equal to 5, R is equal to 6. This yields to R into k minus 1 divided by V minus 1 is equal to 24 by 9 is equal to 8 by 3, which is not an integer. So we are stuck here. So what to do?
Sagarika, not only that, even if there is an integer solution to lambda, we may not be in a position to visualize an incidence matrix of order V cross V admitting of such a combinatorial structure, because we have to physically construct this matrix capital N.
Okay.
Take for example B equal to 8, V equal to 16, K equal to 10, R equal to 5. Then you can easily do the computation and you find lambda equal to 3. Do we have a solution? That means we want to have a matrix capital N of order 16 by 8, having the constant block size 10, having constant replication number 5, such that any two treatments they occur together in 3 blocks.
Okay.
Do we have a solution? It is not very clear right away. These seem to be puzzling issues.
Yes.
Fortunately for us, for many such situations, we have studied, the researchers have studied, and by now we have some knowledge as to what is possible and what not. The solution to the example above is in the negative. There does not exist any solution to this.
It's really interesting. Anyway, what is the special subclass you are referring to? Is that the one with constant lambda? If there are so many issues as to the existence of such designs, what is so special about it? Is it very common in practice? Are there catalogs which an experimenter can consult given the other design parameters, that is B, V, R and K?
SD, I am really surprised by your curiosity to know and criticize. This is a very good attitude. You must ask questions and seek clarifications. Let us go slow. All I can say is that this area of research has created immense academic interest among the design theorists for the last 90 to 100 years, almost. And for your information, Indian design theorists have kept a permanent visible mark in credible research along this area. Let me introduce the special subclass now that I am talking about. It is called balanced incomplete block design. Every single keyword we will try to understand. It is abbreviated as BIBD.
So BIBD is defined in terms of its 4 parameters, that is B, V, R and K, and the derived parameter lambda, right? Maybe not really, since there is also a relation bk is equal to v into r. So basically there are three defining parameters. I am confused. Oh, now I see there are three independent parameters, two others are dependent and derivable from the given three. Am I right, sir?
You may say so, Sagorika. Is it clear why such a combinatorial structure is referred to as a BIBD? We can see that it is an incomplete block design since k is less than v, because you are ruling out the possibility of k equal to v, which means RBD. Therefore, the moment it is an incomplete block design, k is less than v. And the design to start with is binary and proper and equi-replicate. That's why we introduced the design parameters b, v, r, k. But why is it balanced? What is the meaning of balancing? Does it have to do with variance balance? I mean, is it that all treatment effects elementary contrasts of the form tau I minus tau I tau j, these are estimated with the same variance? Does that mean it is connected to start with? If we talk about a BIBD, which is a balanced incomplete block design, we can see that it is incomplete block because k is less than p. It is proper because k is the constant block size. It is equi-replicate because r is the common replication number. What about the wording balancing? And is it a connected block design to start with? So these are the questions that are coming up now.
So you are going fast. Let us try to assimilate this. If we are discussing about variance, we need to assume that the design is connected. Interesting. Does it not follow necessarily from the combinatorial definition of BIBD? What about application of Parksha technique? Oh, I see, it is almost immediate to me. Consider block 1. It has k treatments which are all distinct. Clearly, all treatment effect differences in this block are estimable, and hence all the treatments in the block are in one single equivalence group. Since any two treatments occur together in lambda, which is greater or equal to 1 blocks, we can find another block with at least one treatment common between the two. Hence, through this common treatment, all treatments in the two blocks become connected, and so on. It seems pretty obvious now that all treatments will belong to a single equivalence group, and hence the design will be ultimately connected. Am I right, sir? I am now curious to study from the C matrix of a BIBD.
Okay, let's do that. Note that for a BIBD, now we are referring to 5 parameters B, V, R, K, lambda. Even though, as you rightly said, only 3 of them are independent, the 2 are to be derived from the other 3 using the functional relations, they are parametric relations. So for a BIBD, capital N transpose, it has got all diagonal elements equal to R, and that lambda parameter now comes to play a role in the sense that all off-diagonal elements are equal to lambda. One can see that N transpose is a square matrix of order V cross V. Diagonal elements are all R, off-diagonal elements are all lambda. Therefore, the C matrix, we know the general form of the C matrix, it simplifies to a matrix of the type A into I plus B into J. And you can see what are A and B.
Yes, sir.
Therefore, and because C into 1 equal to 0, A plus VB equal to 0, therefore C matrix is basically proportional to I minus J over V. This suggests that the C matrix has all positive eigenvalues the same. They are all equal, all positive eigenvalues are equal, and that constant eigenvalue is given by A, which is lambda V over K, and using the functional parametric relations, that A is nothing but V R K minus 1 over K into V minus 1. I hope you can see all these things straightforward.
Yes.
These are pretty much easy and routine deductions. One has to use the parametric relations again and again for a BIBD at convenient places to see these obvious simplifications.
I can see all that, and I think it now follows that C plus can be taken as 1 by A into I, and hence the variance of the treatment contrast that tau I minus tau I prime, estimated value of this is equal to the thing that is given here.
Yes, if you look at the expression, you see 2 sigma square over r multiplied by k into v minus 1 over v into k minus 1. So recall that 2 sigma square by r, that is the quantity coming out of a CRD model.
Yes.
If you have a CRD model with application r, that is the expression for the variance of the estimated difference between the 2 treatments.
2 sigma square.
So yeah, so for a BIBD, it is variance of this thing is nothing but 2 sigma square by r multiplied by this quantity.
Yes.
There are 2 things to note. One is this variance is constant. So for all treatment differences, estimates of treatment differences, this variance is constant. That is what is the implication of balance.
Okay.
The design is balanced because no matter what elementary treatment contrast you take, the expression for the variance is independent of the choice of your treatment. Whatever treatments you take, it is the same. That is number 1. Number 2, the expression k into v minus 1 over v into k minus 1 is strictly less than 1 because k is less than v.
Yes.
So you can see that the variance expression is 2
less than-
sigma square by r multiplied by something which is less than 1.
Yes, sir.
Yeah, so in this module 10, we started by understanding the word BIBD, the phrase BIBD, balanced incomplete block design. We are referring to a block design which is incomplete in the sense that k is less than v. Basically, it is a binary, proper, equi-replicate, connected block design with additional qualification of balance. That balance means that the variance of the estimated treatment difference for any pair of treatments is a constant. So because of that constancy, it is called a balanced design. So in the literature, it is also called variance balanced design. So we started with the combinatorial properties of the BIBD, namely Bk equal to Vr, lambda into V minus 1 equal to R into K minus 1. We talked a little bit about the analysis of BIBD, tremendous simplification in the expression for the C matrix, and then we took up some questions where one question was supplemented BIBD, other questions were mostly regarding connectedness, whether the design remains connected or not, as against missing observations. There are still a lot of things to say, namely we have not touched upon the construction of BIBD. How do I construct a BIBD? Are there any catalogs available? What would the experimental do? So there are a lot of questions that are coming up. We hope to take up some of those issues in the next module. Okay, Sagorika?
Okay, sir. Thank you, sir.
Sagorika, let us take up some questions now.
Yes, sir. The first question is, argue that the parameters b is equal to 8, v is equal to 16, r is equal to 5, k is equal to 10 and lambda is equal to 3 do not lead to any BIBD, though the basic relations are satisfied.
Okay, at this stage, there are too many things to know about BIBDs, but at this stage I would suggest that you start working it out.
Okay.
You pretend that there are 8 blocks, each block has got 10 plots, and then you are trying to put all the 16 treatments over there in this design, and you see that you get stuck because of lambda equal to 3. You cannot quite get it, even though the parameters they satisfy the defining relations bk equal to vr, lambda into v minus 1 equal to r into k minus 1. You don't see anything wrong with the parameter relations, even then the design does not exist. You fail to construct anyone. That's a good exercise.
Yes, sir.
What is the next one?
So the next one is, here we need to argue that the union of two BIBDs arising out of two separate BIBDs,
Namely this
namely,
and that.
this thing where I is equal to 1, 2 is also a BIBD.
Okay.
Here B star is equal to B1 plus B2, V, then R1 plus R2, then K, and finally lambda 1 plus lambda 2. These are
So
the
note that
parameters.
interestingly, the two component BIBDs, they still have the same treatment, same number of treatments, and they have the same block size naturally.
Yes, sir.
You have got so many blocks with constant block size k, accommodating V treatments, another set of blocks with the same constant block size k, accommodating the same V treatments.
Yes.
Now you are combining the two. So you are extending the blocks from B1 and B2 to B1 plus B2. You are taking the union.
Yes, sir.
And naturally you are still involving V treatments. Block size is K and R becomes R1 plus R2. So that in the process lambda becomes lambda 1 plus lambda 2 and that it becomes a BIBD. It's a good problem. It's just to see that everything is working fine as you expect.
So the third question is, a new treatment which is denoted by 0 is added as a supplementary treatment in every block of a BIBD with these many parameters. Now here we need to provide an analysis of the data.
It's a very interesting question from conceptual point of view. So as you can imagine, you start with a BIBD and in every block you are using this supplementary treatment. As a result, the new treatment has replication B. Because it is coming in every block. Not only that, the new treatment is coming in a sort of balanced way with all the existing treatments in the design. So if you understand the analysis of a block design, BIBD, particularly computation of the treatment sum of squares adjusted and the block sum of squares unadjusted, you should be able to provide an analysis of this data, supplemented BIBD, by trying to understand what should be the formation of the C matrix now, and then what is the resulting sum of squares due to treatments adjusted. It's a very good fundamental exercise, good exercise, conceptually strong. Okay, what is the next one?
Here is the next one. A treatment is missing in one block of a BIBD and we need to argue that the design is still connected.
Oh, it's a very simple question but it's a bit tricky. You can see that, so there is a BIBD and in one block one treatment is missing. You have to argue that the design is still connected. You know, because this treatment not only occurs once, it occurs R times, and in the BIBD R is more than 1, so there are other places where it is coming. That's how it will be, it will not be totally deleted from the experiment anyway. So you can argue that the design is still connected. Let's see what are the MCQs that we have.
Yes, sir. So the first MCQ is, in a BIBD with these parameters, with R is more than 2, 2 observations are missing. Then the design is necessarily, 3 of the options are there. Will it be disconnected, or it will be connected, or it might be either of the two?
So note that R is greater than 2, so there are at least 3 observations for every treatment, and any 2 observations are missing in the entire design. It is quite likely that the design will still remain connected, but we have to argue it out.
Yes, sir.
What is the next one?
So here is the next one. The statement BIBD is 50% efficient. That means there are the four options are there.
Let's see the options.
The first option is it will produce 50% of the data. The another one is it will produce 50% estimate of error variance. It will produce 50% of the variance for treatment difference estimates. And the last one is none of the above.
Very interesting. Okay, so you should see what is coming up. Okay, good statements. The statements are kind of interesting.
So here is the third question. A BIBD is less efficient than an RBD because the options are the block size is smaller than the number of treatments, though both have same number of blocks. The second one is the number of blocks is less in a BIBD than in an RBD. The third one is BIBD has less number of observations than RBD, and none of the above.
So let's say we know the expression for the for an RBD, the variance of the estimated treatment difference is 2 sigma square by R, period. And for a BIBD, it is 2 sigma square by R multiplied by that constant. That constant is more than 1. So you already know that BIBD has got more variance. It is a constant multiple of what is there in RBD. So you have to only argue out which argument makes more sense in trying to sort out why it is happening. Okay.